a function that calls itself.
That's the definition every textbook opens with, and it's the reason recursion has a reputation, because the sentence sounds like a paradox. If the function hasn't finished running, how can it start again? Won't its variables collide with its own variables? Here's the reframe this whole lesson hangs on. A recursive function never calls itself. It calls a fresh copy of itself. Its own inputs, its own variables, its own place to stand. And the original doesn't restart. It pauses mid-flight at the exact line of the call and waits for the copy to come back with an answer. The machinery that holds a paused function's entire world while any number of copies run is something you already know. When we built stacks, I told you the most famous one of all was running your programs at that very moment. And I owed you the deep dive. This is it. By the end, you'll watch recursion run with the case open, and the bookkeeping I promised is all you'll find inside. Start with no recursion at all, because the machinery isn't special to it. Every function call, every one, pushes a frame onto the call stack. A frame holds three things: the parameters the function was given, the local variables it makes, and the return address, the exact spot in the caller to resume from. Watch three plain functions. Main calls ship. Ship computes a total, then calls charge. While charge is running, the stack holds three frames. At the bottom, mains, paused at its call. Above it, ships, holding that local total, paused at the call to charge. On top, charges, the one actually running. Charge returns. Its frame pops, and execution lands precisely at ship's saved return address, with ship's total still sitting there, untouched. That's the whole trick. A frame is a paused function's entire world, where it was and what it knew. Push on call, pop on return. The function that must finish next is the one called most recently. That's not a new discipline. That's Lesson 6's stack, run by the runtime millions of times a second. Now pointed at recursion, factorial of n. If n is 1, return 1. That line answers directly, hold that thought. Otherwise, return n times factorial of n minus 1. Call factorial of 4, and watch the stack. Frame 1, n is 4. It reaches the multiply, and it can't finish. It needs factorial of 3 first, so it pauses at the multiply, and a second frame pushes. N is 3. Same story. Pauses, pushes n equals 2. Pauses, pushes n equals 1. 4 frames deep. And notice, not one multiplication has happened yet. The whole trip down is just frames stacking up, each holding its own n and its own paused position. Then n equals 1 hits the first line. Small enough to answer directly. Return 1. No new call. Pop. Now the unwind. The frame with n equals 2 wakes up exactly at its multiply. 2 times 1 returns 2. Pop. N equals 3 wakes. 3 times 2, 6. Pop. N equals 4. 4 times 6, 24. Pop, and the stack is empty. Every partial result lived in a frame. The copies from the opening, they were frames all along. There is no magic left to explain. Every recursion that works has exactly 2 ingredients, and you just saw both. Rule 1, a base case, an input small enough to answer directly, with no call. N equals 1, return 1. Rule 2, progress. Every call must move the input closer to that base case. N minus 1 walks toward 1. Now delete Rule 1 and run it. Factorial of 1 calls factorial of 0, calls -1, -2. Each call pushes a frame. No call ever returns, and the stack's memory is finite. The push that doesn't fit kills the program. Stack overflow. The most famous error in programming. Famous enough that the biggest Q&A site for programmers named itself after it. How much room before the crash? Platform dependent, but roughly 1 megabyte per thread on Windows, 8 on a Linux main thread. Python doesn't even wait for the crash. It counts frames and throws a clean error around 1,000 deep on purpose rather than risk the real overflow. And Go is the interesting exception. Go routine stacks start at a few kilobytes and grow as the runtime needs them. Miss Rule 2 and you get the same death with a subtler face. a base case that exists but that the calls never approach. Here's how experienced engineers actually write recursion, and it is not by tracing frames. We traced factorial once to prove the machinery is trustworthy. Now trust it. To write a recursive function, you design exactly two things: the base case and one step written as if the recursive call already returns the right answer. That move has a name: the recursive leap of faith. And it isn't faith, really. It's induction in workflows. If the smallest input is right, and every input is right whenever the smaller one is, then they're all right. Let's use it on a problem with real structure: the size of a directory, the thing du computes when something ate your disk. What is the size of a directory? The sizes of the files in it, plus the sizes of its subdirectories. And the size of a subdirectory is the same question, one level smaller. The definition refers to itself, so the function gets to as well. For each entry, if it's a file, add its size. If it's a directory, add dr size of it. That call is the leap. Base case: a folder with no subfolders never recurses. Progress: every call steps one level down, and the tree has a bottom. And we never pictured a single frame. Factorial is a teaching toy. A loop computes it better, and we'll get to that. This is where recursion earns its keep: data that's nested inside itself. A comment thread. A comment is some text plus a list of replies, and each reply is a comment. The definition refers to itself. A JSON value? Maybe an array of values or an object full of values. A directory contains directories. An expression in a compiler contains expressions. For data shaped like this, the recursive function is barely even code. It's a transcription of the data's own definition. Render a comment, then render each reply, and the nesting handles itself, to any depth. There's a production edge here, too. If your parser recurses over attacker-supplied input, then their nesting depth becomes your stack depth, which is why real parsers cap it. Rust's standard JSON library refuses input nested beyond 128 levels by default. That number is this lesson's crash, priced in ahead of time by a library author. And file this away. A few lessons from now we need trees, the data structure that is nesting. Recursion is the native language there. Now the honest comparison, because any recursion can become a loop, the call stack is just a stack, and you built one of those, so manage it yourself. Keep a stack of pending directories, loop while it isn't empty, pop a path, add up its files, and when you meet a subdirectory, don't call anything, push it. Same algorithm, same answer. The frames became strings you push by hand. So when do you pick which? For straight line processes, the loop wins, no contest. Factorial as a loop is 2 lines, no frames, no depth limit, no call overhead. The recursion bought nothing there, because nothing branches. But for nested structure, look at what the iterative version really is. The same recursion with the bookkeeping done by hand. The runtime was doing that for free, and clearer. So, the rule of thumb. Linear process, write the loop. Branching, nested, self-similar structure, write the recursion. And switch to the explicit stack when depth is dangerous. Attacker-controlled nesting or 1,000 levels in Python. That's not a style choice. That's the platform budget from 2 scenes ago. One beat on a term you'll hear so you can price it honestly. Look at Factorial's recursive line. N times factorial n minus 1. After the call returns, there's still work pending. The multiply. So the frame must survive. But suppose the call were the function's very last act, nothing pending after it. Then the frame holds nothing worth keeping, and a smart compiler can reuse it instead of pushing a new one. Recursion in constant stack. That's a tail call, and eliminating the frame is tail call optimization. Now the status report, because this is where people get burned. Scheme guarantees it. Looping in Scheme literally is recursion. JavaScript wrote it into the spec back in 2015, and the engines mostly never shipped it. Safari did. The others backed out. Python rejects it on principle. Its creator wants stack traces to show the real history. And Go makes no promise either. So the working rule for a back-end engineer is blunt. In Python, JavaScript, Go, Java, assume every call costs a frame. If the depth is linear, write the loop. Way back in Lesson 1, while pricing memory, I made a promise that a function recursing n levels deep is using order in memory, even though no line of it ever allocates anything. You can now see exactly why. At the peak of factorial of n frames are alive at once, each holding parameters, locals, a return address. Recursion depth is an allocation. From today, price it like one. But here's the flip side, and it sets up the next two lessons. Depth depends on how fast the problem shrinks. Shrink by 1 per call, like factorial or walking a list, depth n. That's the dangerous kind. Shrink by half, depth log n. Binary search, written recursively, is 30 frames against a billion elements. Harmless. And merge sort, next lesson star, recurses by halving 2. A million elements, about 20 levels of frames. Nothing. So the recursion to watch is the -1 kind. The halving kind barely touches the stack at all. One trap left, and it isn't about the stack. Fibonacci. Fib of n is fib of n minus 1 plus fib of n minus 2. 2 recursive calls, which means the calls don't form a chain anymore. They form a tree. Watch fib of 5. It calls fib of 4 and fib of 3, but fib of 4 also calls fib of 3. So fib of 3 runs twice, from scratch, identical work. Fib of 2 runs 3 times. Fib of 1, 5 times. The duplication compounds at every level, and the tree roughly doubles per level. That's the exponential rung from Lesson 1's ladder, the row where the universe ends first. Fib of 50, written this way, makes tens of billions of calls, minutes of CPU, for a number that fits in 8 bytes. And here's the subtle part. The stack is fine. The tree is explored one branch at a time, so the depth never beats in. Exponential time, linear space. So the lesson is sharp. Recursion describes a problem. It does not promise an efficient solution. The fix, remembering answers instead of recomputing them, is called memoization, and it gets its own treatment in the patterns course. For now, learn the smell. 2 recursive calls over overlapping inputs. Audit before you ship. So the case is open, and the magic is gone. A call pushes a frame. Parameters, locals, return address. A return pops it. Recursion is just frames of the same function, and writing one is 2 design decisions, a base case and 1 trusted step. Depth is memory. Halving makes depth cheap, and 2 innocent calls can hide an exponential bill. Next lesson. This machinery meets the most studied problem in computer science, sorting. Because the fastest general-purpose sorts are recursive at heart. Merge sort splits the array in half, trusts each half to come back sorted, and earns everything in how it puts them back together. 20 frames deep at a million elements. Quicksort makes a braver bet. And the sort your standard library actually runs is a battle-tested hybrid of these ideas. Merge, quick, and how libraries really sort. See you there.